He's going to be talking about singlet contrast magnetic resonance imaging. So I'm looking forward to this. Go ahead, take it away, James, whenever you're ready.
Okay, yeah. Thanks very much for the introduction and for organizing this lovely conference. I'll talk to you today about the singlet-contrast magnetic resonance imaging, and I'll start with a picture of this molecule that, oh, hold on one moment. I've been told that I can use oh, there we go. That's much better. Okay, I'll talk about this molecule fumarate today, and I talk about this molecule a lot, and I'm sure some people are thinking, man, when's he going to stop talking about fumarate? But I hope I can convince you that it's an extremely interesting molecule with biological relevance, and it's interesting from like a nuclear spin standpoint. So I'm going to quickly recap a couple of things that I talked about. I had a talk a couple of days ago, and this slide is just going to be a recap of some of the things I mentioned there. So apologies if you saw that. This is just going to be a repeat. But for anybody who didn't, I can let you know that fumarate is somewhat regularly used in dissolution dynamic nuclear polarization experiments, where the carbon-13 spins are polarized. And the reason for doing this is that in the body, fumarate can be converted to malate or malate, and this metabolism can be observed in vivo with hyperpolarized magnetic resonance imaging. So the contrast in these experiments comes from this idea that fumarate does not penetrate healthy cells. So you have like a cell membrane, and the fumarate doesn't pass through that very rapidly. It's an extremely slow process. So it has no access to the cell and no access to the enzymes that will metabolize it to malate. But if the cells are ruptured, so if the cells are dead and they open up, the enzymes can leak into the extracellular space, excuse me, and you can observe conversion to malate in that case. So cell ruptures, enzyme leaks out, suddenly you can see this metabolite appear in the spectra. So this is used for imaging tumor response to treatment, and for imaging things like myocardial infarction. This has been demonstrated. I've been told that a clinical trial is actually underway with hyperpolarized fumarate, although I don't know where that has got to with the current coronavirus situation. Maybe that was halted, I'm not sure. But it's extremely exciting, the fact that this will hopefully be applied in the clinic soon. So in parallel to those efforts, we've been working on, and what I talked about on Monday is that we can now form fumarate via FIP, and we can polarize the carbon-13s, and now I think we're at the point of being very competitive with dissolution DNP, because we can produce hyperpolarized purified solutions, and in our most recent work, we're showing things like metabolism of fumarate to malate with FIP polarized fumarate. Okay, so that was all about carbon-13 and doing carbon imaging. And if we take a little look at this table, I've drawn up some comparisons between doing hyperpolarized imaging with carbon and proton. So why is it that the majority of imaging uses carbon? Well, the T1 times are relatively long compared to protons. So if you're an aqueous solution, protons can relax in the order of just a few seconds, whereas carbon-13s might be much longer lived in the tens of second time scale. Now that's going to be enough time to produce the metabolite, transport it over to a person or an animal, inject it, it migrates to the area of interest, undergoes some metabolism. All of that takes time. So this is really important. Background signals, well, they're pretty much non-existent for carbon-13, but in proton images, of course, there's water and fat throughout the body. So there's a significant background. And chemical shift dispersion is another one. If you want to see metabolism, it's, I suspect, much easier to do that in carbon-13 spectra because, I think I have a little, yeah, here we go. Here's just a visual representation. The carbon-13 chemical shift dispersions in the order of hundreds of ppm, but for protons, it's really much, much smaller. So if you're looking for peak shifts, that can be a lot harder to see if you don't really have high spectral resolution. On the other hand, carbon-13 MRI has a number of drawbacks. Sensitivity is low, even by NMR standards. So I say that proton sensitivity is relatively high. In this case, all other factors being equal, and if they're polarized to the same degree, I believe proton should be 16 times more sensitive than carbon. you get a factor of 4 from the faster precession, and another factor of 4 because they're just more magnetized. They have a higher gamma. Equipment availability, I guess just about every commercial MRI scanner in the world has proton pulse and detect capabilities, and isotopic abundance. There's no need for isotopic enrichment with protons. And finally, I've been told, I'm assured that you can have higher spatial resolution with proton imaging because they respond better to field gradients, right? They have a high gamma, so they're more responsive. I think this is the big one, though. I think this is the really big one. This is why heteronuclei, i.e. nuclei that aren't protons, are favored for in vivo imaging. Okay, so, well, we'll talk about a possible solution to that. I have a quote here: para-hydrogen-induced polarization is the best hyperpolarization technique. I think there's probably, there's just about no doubt over that. But maybe we don't often think about why that is true. Of course, yeah, para-hydrogen is very cheap and it's easy to use. But one of the biggest advantages is that para-hydrogen is extremely long-lived. So we say that this dihydrogen molecule, when in a nuclear spin singlet state, is NMR silent. And it doesn't interact with like electromagnetic fields. Now that state can be extremely long-lived. We regularly produce this stuff and store it in canisters for days or weeks, and we flow it through tubing between labs and whatnot. It's an extremely useful property of this source of hyperpolarization. And the idea is that we bring it to our experiments. We're all doing this. We bring it to our experiments, and at some point in the experiment, we will liberate some hyperpolarized signals from this non-magnetic state. Over here, I've just quickly thrown in a depiction of that in what is probably a non-chemically real situation, but the principle is quite clear. We take our hydrogen, we add it to a molecule. In this case, if we're at high field, a chemical shift difference between these protons will break the symmetry, and from that we release these hyperpolarized, what we would call Pasadena signals. Okay, so in principle, we have quite an interesting molecule here, because if we can hydrogenate starting material with para-enriched hydrogen and form fumarate, well, there are no other nuclear spins in this molecule. So if we ignore all of the carbon-13s at natural abundance, we're just looking at about 96% of molecules with no carbon-13. There are no other spins, and so the proton singlet state remains an exact eigenstate. And the idea is that, well, Alexei Yershov has shown that proton singlet state in dimethyl fumarate can be very long-lived in deuterated solution, like hundreds of seconds. And we are hoping, and we don't know this is really unknown at this point, we're hoping that might also be relatively long-lived in aqueous solution. So Alexei also did work with the dimethyl malleate form, so the cis isomer of this molecule, and showed that in solutions where it's 50-50 water and deuterated methanol, the singlet lifetime on those protons can still be over a minute. So we're sort of, at the moment, we just hope that maybe the same is true for fumarate, although we don't know that. And so now I can describe the principle of the experiment. So we form fit polarized fumarate. The protons are in this long-lived nuclear spin singlet state, and at some point, this molecule will undergo metabolism to form malate. And if we do that in D2O, we do this for simplicity for this demonstration, so that we have deuterons, but we can ignore them for the nuclear spin dynamics. We end up with two protons that now have a chemical shift difference, and so we've broken the symmetry between them in that way. So here's what the spectra look like. If you did this with just a normal hydrogen gas, you end up with here's like a water peak, and you have two resonances, two doublets from those protons. And if you did this with para-hydrogen, then you get this characteristic anti-phase pattern, the up-down lines that we're so familiar with. These are obviously scaled arbitrarily. These lines are enormously enhanced. So in this style of experiment, we in principle overcome the problems that we outlined with hyperpolarized proton imaging. The rapid relaxation problem will hopefully be solved by the protons being in a long-lived state. The proton background, well, the singlet state between these protons is going to be unaffected by RF irradiation. So we can saturate any background signals coming from magnetized protons in the sample, and this should remain unaffected until it undergoes metabolism, and then some peaks appear. And so the final thought is that this should be insensitive to the problem of the spectral resolution of proton images, because we're not looking for peak shifts. There should be really nothing to see until this happens, and then these enormous peaks should appear in the spectra. And so here I say we need a pulse sequence that will rephase these signals. So create in-phase signals from these, because we can't do imaging like this, because if you apply any gradient to these anti-phase signals, they'll just be broadened, and then you just cancel all the signal. And the second thing our pulse sequence should do is remove background signals from the water. Okay, well, here's a little cartoon depiction of the whole experiment that Lauren Astagis has drawn up. We start with fumarate, and the protons are in a singlet state, and there's magnetized water just floating around. We add water to this molecule, and enzyme catalyzes that, and now we've released our singlet state as these into ZZ order. And now we want to apply one of two pulse sequences that should remove magnetization from the water in the background and give us in-phase observable magnetization on the malate protons. Okay, so to test these pulse sequences, to evaluate them, we work with thermal equilibrium magnetization at first. We don't want to be optimizing pulse sequences with hyperpolarized samples. It's inconvenient to do that with parahydrogen because it's such a transient thing. You're trying to optimize a pulse sequence, and you have relaxation that you have to take into account, and bubbling and whatnot. So for this purpose, we work with thermal equilibrium molecules. So we have our malate, and we prepare this state of I1z.I2z spin order between the two protons with this sequence, which I think is colloquially referred to as the reverse Sarkar sequence. And after applying this and generating I1z.I2z spin order, we can then apply one of two options, the out-of-phase echo pulse sequences that we're investigating, and we'll just vary the tau delay in those sequences. And what we see is oscillating signal coming from the protons in malate. And well, it turns out that oscillation is maximum at 1/4J, so we can take this as our maximum value, 20 milliseconds. Okay, now we come to do a real experiment where we will take our precursor and hydrogenate it with para-enriched hydrogen. I've been asked by Igor to stop saying para-hydrogenate because that has a very technical and different meaning. And we form fumarate, and then we're going to shuttle that over to a magnet where we have an NMR tube containing our enzyme solution. So let's see. So we do that, and we have that should catalyze our enzyme conversion. So we do that, and what we're going to do is just apply a 45-degree pulse again and again and again over the course of time. And oh, okay, yeah, well, all right. Just in a moment, this axis will make sense. There you go. That's across there. We do this with a 45 pulse again and again and again, and then we repeat the experiment and use the out-of-phase echo 45 sequence. And finally, we do the same thing with this selective 90 sequence. Okay, and so what we see is just a signal decay. And the reason for that is that each time we're applying this pulse sequence, we convert close to all of the hyperpolarized spin order into observable magnetization with each application. So what we see between each data point is all of the malate that formed since application of the previous sequence. So these are being applied every 4 seconds. So it's as if we're seeing the malate that formed in those previous 4 seconds. This is contrary to a lot of like carbon-13 images of this, carbon-13 traces of this metabolism, where people use small flip angle pulses. And in that case, you see a characteristic build up and decay of the signal. Well, that's the difference here. That's why it just simply decays in this case. And I highlight this to show here's like one of the individual spectra. Well, in this non-selective out-of-phase echo 45 sequence, we polarize both proton resonances in malate, and we, well, to a good degree, cancel out the water signal. And in the selective 90 sequence, we're just exciting this resonance, and we don't even see the water signal in the spectra anymore. So it appears that all appears to be working. We seem to have, we have in-phase hyperpolarized proton signals, and we seem to be canceling our background. Okay, so now we can actually try using this for imaging. So here's the setup that we have, where we have a 30 ml NMR tube containing water, and inside that is a 10 ml NMR tube with a phosphate buffer solution, buffering the enzyme, and we're going to inject our hyperpolarized sample into that. And that's why it's this yellow color, because well, the catalyst in our system gives this nice yellow color to the samples. For the imaging demonstration, we'll use the out of phase the selective 90 out of phase echo sequence. So we'll just pick this one to do this. So we'll apply that to the system, and then we'll use a flash sequence to collect an image. We repeat this whole sequence a number of times. So it's like we apply that, we collect an image with the flash sequence, and then we repeat the whole procedure. And here's what the results look like. So here are some axial images where we have like the water background signal and our hyperpolarized signal from the malate in the 10 ml NMR tube. You can see here the capillary. We have a sagittal image here, and then across here you see a time series where these images were collected every 12 seconds, and you can see those malate signals decaying. And that's a combination of relaxation of the hyperpolarized spins and the metabolism going towards completion. It's a combination of those two effects. That's why the signals are decaying. Huge thanks to Dr. Stefan Knecht, who has been there at every single step of this project and all of our other work with fumarate, and really took the lead on the whole imaging front. And so now we have this question of, if this is to be used in real systems, what is the singlet lifetime of the protons on fumarate in water? And at the moment, we don't know. We'll hopefully measure that very soon. Although I would say that even if this molecular system itself isn't practically applicable, Lauren Astagas has just put a paper online on this new NMR journal showing geminal hydrogenation, and there are other examples of geminal hydrogenation published previously. And systems like this, where the protons are much closer in space, could absolutely support long-lived singlet states, even in aqueous protonated solutions. So I think there is absolutely promise there for the future. And I would like to finish with a nod towards this work by Aurélien Bornet and Sami Genan, who performed a very similar experiment using dynamic nuclear polarization a few years ago. And in this experiment, they magnetized the protons with DNP, and they observed the same enzymatic conversion. And the experiment was to measure the lifetime of singlet state in malate maintained by spin locking. This is extremely similar work, and our work certainly follows on from this. And what we've done is demonstrate that this is possible with parahydrogen, and we've taken it that step further to actually use this to perform imaging. The benefit of using parahydrogen, we're always talking about like the cost saving and the ease of doing experiments. And in this type of experiment, there's another important benefit, which is that in the parahydrogen case, we start with population on fumarate entirely, or to a good approximation, fully in the singlet state. And that gives us, let's say, a relative signal intensity of 1. But if you use DNP to do this, the state that you populate is, well, say the T plus state or T minus, one of these triplet states. And then even if TS is extremely long and you don't have this conversion of spin order from the triplet manifold to the singlet manifold, well, T1 can be relatively short. And if you spread the population within the triplet manifold, if it's redistributed, the signal intensities that you can get out are reduced. So even if you have 100% of the population within the triplet manifold, well, that corresponds to negative 1/3 singlet order, and the signals are correspondingly, 1/3 of the maximum size they could be if you'd started with pure singlet order. And so with that, I'd like to finish and thank all of the people here and thank you for your attention.
All right. Thank you very much, James. That was awesome. We do have a few questions, as you might expect. So I will dive into a couple of them here. Let's see. First, can one really effectively saturate the water background in an imaging experiment safely? I think he's probably speaking clinically.
Yeah, well, that's certainly a question for people who do clinical imaging. The fact that question's being asked makes me think, no, perhaps not. We don't do that in this work, though. It's not necessary. We actually, I think, oh, maybe I can jump back to, here we go. We don't actually saturate the water background. We just use pulse sequencers that will either selectively excite the resonances that we're interested in seeing, so we don't even excite the waterline, or we use pulse methods to negate any signals that arose from magnetization and selectively excite signals that arise from ZZ order. So in this case, we don't actually need to do that.
Okay, good point. Next, a number of the decays appear bi-exponential. Can you comment if this is rather because of the chemistry or because of different decay rates of different spin order?
Oh, that's a good question. Let me think for a moment about that. I assume that that's in reference to these decays. This is more likely just an effect of. This is more likely to be just an effect of putting the sample into the magnet.
Right is yes, those. Sorry.
Oh, yes. Yeah, it's probably just an effect of putting the sample in the magnet and having some sort of convection within the sample while applying the pulse sequences, I would guess, rather than being two different types of relaxation going on.
You may have touched on this, when you were comparing DNP preparation of the singlet state versus with parahydrogen, sort of looking at what can be achieved in theory. What's the difference in efficiency that you might expect in the two cases, or how much better is using parahydrogen?
Yeah, well, it's a little bit tricky to give like a really simple answer to that. If you start with full population in the singlet state, and then so your fume rate is fully singlet polarized, and you have conversion to malate, and you say that gives you like a hyperpolarized signal intensity of 1, then if you have the DMP case where you fully populate just this triplet plus 1 state, you can have the same. You also have your like maximum. You can have a maximum signal intensity of. Well, let me think for a moment. Actually, it's probably a little bit. No, it's even more involved than that, I'm afraid. Okay, yeah. Hold on one moment. Let me think. The case is simple if you just assume rapid T1 and very long TS. Then it becomes relatively simple because you have rapid redistribution within the triplet manifold. If you started fully polarized here, and then the signal is simply 1/3 of what it would be if you had a singlet state to start with. But I think it's a little bit more involved than that, because if you're fully magnetized in this state and you have relatively long T1, I think the signals that you acquire can be larger than if you start in a singlet state and rely on generation of ZZ order.
Okay. All right. Okay, I think that's it. Thank you very much, James, for a great talk. I will start the process of transitioning over the next speaker.
Thanks very much.